Please don't forget to like, subscribe, and comment. Thank you so much.
Join us at Like Learning School and experience a transformative education journey. Visit our website at www.likelearningschool.com or contact us at +2348085095144 to learn more and get started today.
And see that for Kirchoffs' first law, which states that sum of current into a junction is equal to sum of current out of the junction, or sum of current in to a junction is equal to sum of current out of the junction. Particularly, it always applies at junctions. For instance, this I flowing into this junction must be equal to all the current, sum of the currents flowing out of the junction. That's I1 flowing into a junction must be equal to I2 plus I3. So we can see that Kirchoffs' first law, or what we also call Kirchoffs' current law or charge law. So Kirchoffs junction law, Kirchoffs' first law, Kirchoffs' current law, Kirchoffs' junction law, they are all talking about the same thing. And it's all about the fact that total current into a junction must be equal to total current out of the junction. And we can see that it is the law of conservation of charge. It's the law of conservation of charge. Because the total amount of charge entering a point must be the total amount of charge exiting the point for the charge to be conserved. In other words, if for instance you have 1 billion electrons entering a point in a circuit in any given time, then 1 billion electron must exit that point in the same time. One of the ways we can test that is to connect ammeters along a given path that is in series. For instance, you connect an ammeter here, and then you connect another ammeter at another point in series with it, and maybe at another point in series with it. You discover that the ammeter reading at this point will be equal to the ammeter reading at the other point and the other point, so long as they are in series, which shows you that the current is conserved, or the amount of charge passing is conserved. In the same way, if you connect an ammeter reading here to measure I1, and you connect an ammeter reading here to measure I2, an ammeter reading to measure I3, I2 plus I3 will definitely give you I1, to show you that at this point, this junction Q, the charge is conserved, meaning that the charge coming in, the total charge coming in is equal to the total charge going out, so charge is conserved. So Kirchoffs' first law is the law of conservation of charge. The amount of charge entering a point or a junction must be the amount of charge leaving the point or that junction for the charge to be conserved. Or the amount of current entering a junction or a point must be equal to the amount of current leaving that point. So that's about Kirchoffs' first law, which of course is the law of Kirchoffs' current law or Kirchoffs' junction law. Now the second law, which of course we call Kirchoffs' second law, is the fact that in any given loop, the sum of the EMF must be equal to the sum of the PDs. The sum of the EMF must be equal to the sum of the PDs in any given loop. Any given loop, like you walk through this loop, or you walk through this loop, walk through this loop, or you walk through this loop. Any loop is a path through which current can flow. Current can flow through here, it can flow through here, or it can even flow through here. Any path through which the current can flow is a loop. And in any given loop, when you add up the EMFs, it must be equal to the sum of the PDs. We've talked about that earlier. Now, Kirchoffs' second law is the principle of conservation of energy. Because if a charge of, say, 1 coulomb moves around a circuit, it's going to be gaining energy anytime it meets an EMF, a source of EMF, like a battery. The charge will gain energy. But when it passes through any component, it loses the energy. So it gains energy, the charge, for instance, a charge of 1 coulomb that flows through a loop. Let me illustrate it here. We have a charge of 1 coulomb that flows through this upper loop. If you start from here, this is an EMF, it gains energy. Now this is a component, it loses energy because of potential difference here. It also loses energy because of potential difference here. So it will come back to have the initial energy it started with, because energy is conserved. So if it started with an energy of 1 joule, for instance, and gained 5 joules by passing through this EMF. Remember, it had an energy of 1 joule. Now when it passed through the EMF, it gained an energy of 5 joules. So altogether it will have an energy of 6 joules. So now when it is moving around a loop, now on passing a potential difference, which of course is provided by a component, it will lose some of the energy, and then it passes through another potential difference, it loses some of the energy. Now by the time it's returning to the power source, which is the EMF, it will have the initial energy it started with, which of course is 1 joule. In other words, it started with 1 joule. On passing the electromotive force, EMF, it gained additional 5 joules, making it 6 joules. And then as it moves around this loop, for instance, if it passes through this PD, potential difference, and it loses 3 joules, and then it loses another 2 joules here. Remember, it was 6 initially. As it left this EMF, it was 6. As it left the EMF, it had 6 joules. It loses 3 joules across this PD. It loses another 2 joules across this PD. So by the time it's going back to the power source, it will be left with that 1 joule it started with. So energy is conserved. From 1 joule, gained 5 joules from the EMF to become 6 joules. Going around the loop, loses 3 joules to this PD component, this component with the potential difference across it. What will be left will now be 3 joules. 6 joules, losing 3 joules will mean 3 joules will be left. It meets another PD, it loses 2 joules. So 1 joule will be left. So as it's coming back to the power source, it has the initial 1 joule it started with. So energy is conserved, whether it is moving around the outer loop, or the upper loop, or the lower loop, or the other one loop. In all loops, in any given loop, energy is conserved. So for instance, if a charge of 1 coulomb moves around the circuit, it gains energy as it moves through each source of EMF. The EMF gives it energy, and then it loses energy as it passes through each PD. So if the charge moves all around the loop, so that it ends up where it started, it must have the same energy at the end as at the beginning. If that doesn't happen, we will be creating energy from nothing, simply by moving a charge around a circuit, and that is not possible. So Kirchoffs' second law is the conservation of energy law. In other words, energy gained by passing through sources of EMF must be equal to energy lost when it passes through components with PDs. Energy gained when it passed through sources of EMF must be equal to energy lost when it passed through PDs. For instance, in this outermost loop, as it is moving, it gains energy when it passes through this EMF, E1, Now when it enters E2, it also gains energy, but it loses the energy at this PD to come back with the initial energy it started with, and then the cycle continues. That's the way it is with Kirchoffs' laws. Remember, the first law is about conservation of charge. Total current into a junction is equal to total current out of the junction. Charge is conserved because current is the rate of flow of charge, so charge is conserved. The second law is about conservation of energy. Total EMF in any given loop, the total EMF must be equal to the total PDs. So as it moves around the loop, it gains energy when it passes through an EMF, but loses energy when it passes through a PDs in components, or PDs across components. And so it comes back, it returns to its original position with this energy it started with. That's that.
Basically the Kirchoffs law, which you already know, right?
Yes.
Okay, so when you have something like this to analyze, because basically you are required to find I1, which of course is the same as this, I2, I3, are there some V's that are not given, then I3, just the I's, all the V's are given. So you can walk from one loop to another loop, just develop formula and equations based on the different loops. Imagine we are walking around this upper loop, the upper loop. You know Kirchoffs' second law, round a loop, the EMF is equal to the PDs in any given loop. The sum of the EMFs you pass around that loop is equal to the PDs. Now, why do we say sum of the EMF? Because sometimes the EMF might be more than one. Like this, if you have EMF, several EMFs, you need to be careful when you have several EMF. Like this EMF, I can call it this first one A, this second one B, this third one C, E, D. There are 4 EMFs in place. Whichever one you're going to start with. If you're going around clockwise, maintain the clockwise. If you're going around anti-clockwise, maintain that. You will get the same answer. Assuming I want to go around clockwise, starting from A, which is the reference EMF, like the starting one. So I will give it positive because I'm starting from A, positive. By right, it should move from positive to negative. But if it is meeting negative, it will repel. So that's why it's going to be plus minus 2. I mean, A is plus 2. Now when it is meeting B, it is going to be minus 2. Now from B, if it is now going to C, you are looking at C with reference to A. All of that are with reference to A. So it started from positive. It should be meeting negative. So it's a normal flow. Also to D, with reference to A, is meeting negative, which is the normal flow. So you also add. So once it is the normal flow, that is positive to negative, you add. But if it is like positive to negative, you add. Positive to negative, you add. But if it is positive to positive, you subtract. They are pushing back. So this will now be the total EMF. So 2 plus minus 2 is an opposing EMF. What you call opposing? This B is an opposing EMF. But C is in the proper direction because it is positive coming to negative. D is also in the proper direction because it is positive coming to negative. So you can now get the total EMFs. Because when you have several EMFs, you need to follow that down. Now, this question is easy, just one EMF in a particular loop. So we don't have much to do with several EMFs. So can I just zoom out a little bit? Just one EMF. So if we are following the upper loop, we can walk around the upper loop or walk around the lower loop. By the way, the directions of the current is not shouldn't even bother you, because if a particular direction is given, if you eventually get negative, it means it's supposed to go the other way around. Okay, first of all, then we know that conventional current direction is from positive to negative. So anytime you start from positive, just run around until you get to negative. Anytime you start from positive, run around until you get to negative. But that doesn't mean that that is the way the current will actually flow. Yes, it's possible that even though we think the current is going to flow up here, around here, it may actually be flowing down. Yes, we will find out that. It's an interesting and exciting analysis. So, but then the first thing you need to do is follow the conventional current direction in any given loop. Like I want to go around the upper loop. From the positive, I trace round. Do you know I can also go around the outer loop if I wanted, but it's more complicated. So let me just go the upper loop. So current will go like this way, and back to the negative. If I want to go through the lower loop, also from the positive, current will go like this and back to the negative, isn't it?
Yes.
So let's go. Applying Kirchoffs' second law is interesting from Kirchhoff because we develop several equations, or maybe a few. Second law, that is the way we'll be solving anything that has to just Kirchoffs' law, first and second law. You know, okay, we can, the simplest one we can use will be the first law. You can do first law, you can do second law, but let's look at the first law, which is easier to apply at junctions, you know. First law is about current, yeah? From Kirchoff's first law, at junctions, you know what I mean? Like at the junction P. At junction P, what can you say here?
I1 and I2.
We give you I3 because total current into a junction is equal to total current out of the junction. So we can just establish the first equation. I3 is equal to I1 plus I2. Call that equation 1. But we are not certain that all of them are flowing in the direction given. But that shouldn't be your problem. Once you finish, anyone that is actually in the opposite direction will show itself. Okay, we can also apply it here. If you wanted to, you can call this one. Okay, we already have something about I1 and I2, so there's no need duplicating it here, isn't it?
Yes.
Okay, so that's from Kirchoff's first law. First law is about current at junctions. Second law is about voltage and EMF in a given loop. So from Kirchoff's second law, considering the upper loop, let's consider the upper loop. That's the loop that is upper. Considering the upper loop, we have this upper loop, isn't it?
Yes.
The only EMF in that upper loop is this. Is it not?
Yes.
So this 6 volt EMF is equal to all the PDs we meet when we moved round. You know, there's a PD here, because this is the upper loop. There's a PD here and there's a PD here. So sum of EMF 6 equal to sum of the PDs, PD here and PD here. So
Okay, that's true.
yeah, so I can say the EMF, let me just write it. Sum of EMF, let me just write EMF is equal to sum of PDs in any given loop. That's what it means, isn't it? Okay, so the only EMF on that loop is 6. That's on this upper loop. You get that?
But how is he connected his shoes with this?
Pardon?
How is he connected his shoes with this?
Beautiful. For your information, we are not necessarily saying that this is in series with this. A loop does not have to have all its components in series. Take note of that. A loop doesn't have to have the components in it in series. I'm not saying that. I'm just saying that a loop is any path through which current can flow. because current can flow like this. So it's a loop. Current can also flow like this. So it's a loop. Current can also flow like this because there's an EMF here. Current can also flow like this. So this is a loop. There are actually 3 loops in this circuit. A loop, components in a loop don't all have to be in series. A loop is just any possible path that current can flow. In fact, that's why, the loops, as if you have many loops, then you definitely have components that are in parallel. Because in parallel circuit, it has choice of routes. It can flow through many routes. You get that?
Yes.
Just for your information and for a simple revision, you remember all of this.
Yes.
Parallel circuit, current has a choice of routes, so it can flow through different routes. It doesn't mean that everything here is in series. They are not. This and this are in series, quite alright.
Yes.
Okay, let me give you a diagram that shows. What I was trying to say is these are in series because the same current flows through them. How do we know things that are in series?
If there are no junction between them.
If the same current flows through them, the current did not branch out
Did not split up.
or split into another part while flowing through them. But watch this one. Look at this. This diagram, I can zoom it in a bit. It can flow like this, right? It can also flow like this, right? It's only one cell, so there's no other way current will come from down. So it can flow like this. That's one loop. It can also flow like this. That's another loop. Do you think this resistor here is in series with this resistor here?
No.
Why are they not in series?
Wait, this resistor.
6 ohm resistor and 2 ohm resistor, are they in series?
No. You don't have the same current.
They don't have the same current flowing through them. Even though they are in one particular loop, they don't have the same current flowing through them. A loop does not mean that the components there are in series. It's just any particular path through which current can flow. Now, for components to be in parallel, that's another thing you need to know. For components to be in parallel, I don't know if I explained it here, I didn't. Okay.
Their voltage must be the same.
Their voltage must be the same, and
Yeah, correct.
when currents branch out, they must meet together. This is the illustration I can give you on that. For instance, from a junction here, and current branches out, passes through this path, they must meet together to continue their flow. So this component, let me call it A and B, are in parallel just because the current that split at this junction flow through the different routes and still recombine. If they don't all come back, they are not in series. They are not in parallel. This is what I mean. You will appreciate it. Let me see how I can illustrate this. If they meet up here, okay. Let me bring up another path. I'm coming. Take it. Let me call this one E. Okay, let's go now. Which ones are in parallel? I like this, the way. So I can just indicate junction. I think the best thing for me to do is zoom this thing out, so I'll be able to see this better. Even the diagram is not properly drawn, but it can help us to explain what we mean. Zoom out a bit. Okay, so we just name these junctions. I will call it junction P, Q, R, and T. P, Q, R, and T. These 4 junctions. P, Q, R, and T. Good. Which components are in parallel and why?
A and B.
A and B are in parallel because when the current split at Q, it went through this path, and met up here. That's the only time the voltage here is equal to the voltage here. You know, voltage is the same everywhere components are in parallel, isn't it? Okay.
And this entire combination is a parallel with this.
Excellent. You can flow through these routes up to here. They are in parallel with this.
You can assume this parallel resistors are one resistor.
Exactly. Exactly. In fact, EBD together are in parallel with C, because current can flow through here. So no, honestly, let's get it right. E, AB, and D together. That's E, then AB and D together are in parallel with C.
Yes.
Because A and B
Are parallel together.
can be put together
As one resistor.
Exactly. So that's the point I wanted to make. So back to our analysis.
Okay.
So beautiful analysis. Let's move on. Considering the upper loop, which is this upper loop, right? The EMF is equal to all the PDs. So what's the EMF? The only EMF is 6, isn't it?
Yes.
So 6.0 is equal to all the PDs. This is a PD and this is also a PD, isn't it?
Yes.
And you know voltage is current times R, isn't it?
Yes.
V is equal to our PD, which is V, is equal to IR. So the PD for the 30 ohms resistor will be what?
The PD for that's 2 volts.
No, the PD on the 30 volt resistor. Just walk around here. It will be 2 anyways, but let's just walk around here. We may not even give it any value.
Okay, that's
30
I3
30 I3, interesting.
or 30 I2 plus I1.
Exactly. So
Plus
30 I3. Then
that you can substitute.
exactly for something plus the PD here.
Yes, that's I1.
10 I1, you mean? Because it's I1 that's passing through it.
Yeah.
10 I1. That's 10 I1. Did you get that?
Yes.
So we can call that equation 2. First of all, equation 1, we got equation 1 by applying Kirchoffs' first law
Yes.
at a junction. The current entering into a junction is called current going out of the junction. So I3, the outgoing current, is equal to I1 plus I2. Equation 1. Equation 2, we have applied it by considering Kirchoffs' second law on the upper loop. This upper loop. EMF is equal to the PDs. PD here is IR, which is 30 I3 plus 10 I1. So that's that. So we can consider the lower loop and apply Kirchoffs' second law too, from considering the lower loop.
That's 30 I3 equals to 2 volts.
Exactly, because this is the only PD here. Is it not?
Yes.
This is the only PD here. So 30 I3 or 2 volt, 2.0, because this is the only EMF. The only EMF on that inner lower loop, which is here, is 2 volt, 2.0. It's equal to the sum of the PDs, and the only PD is also 30 I3, isn't it?
Yes.
So it's equal to 30 I3. You can call that equation 3, isn't it?
Yes.
We have all that. We can easily get I3 here.
Yes.
So let's just start solving these 3 equations. Sometimes you might form several equations. In fact, the thing about Kirchoffs analyzing circuit is just solving simultaneous equations.
That's what electrical engineers do.
Exactly, just solving simultaneous equations, plenty of them.
But is it possible they can give you more than two cells?
Yes,
They can give you more than 2.
yes, of course. If they give you more than 2 cells, you just follow that principle that a voltage here, a voltage, the opposing ones minus, the ones that are in the right direction plus.
Wow.
Yes, you can have more than 2. And it is not any big deal, just follow through.
Because I saw on YouTube, like in America, I think they represent their resistors.
With this thing, yeah, exactly, that's how it is done. It's the same principle.
You were doing some work, so it was crazy.
It's just the same principle. It's circuit analysis. It's the same principle. They are same basic principle. Same basic principle. Okay, so you can quickly get I3. So I3 is equal to 2 over 30.
Then you can substitute.
So let's just leave it 2 over 30 amps. We can substitute into any of the equations. Which equation can we easily substitute it?
Into this one.
We can substitute it into this one. And okay, we make I3, sorry, the formula here.
Yes. So CC block.
All right. So if we substitute I3 here, we can easily get I1, isn't it?
Yes.
So let's go. From substituting I3 into equation 1. Because I want us to complete this to see if we get an opposing one instead of the direction we got it. Substituting I3 into equation 2. We are substituting into equation 2 now.
Yes.
So we're going to write 6.0, right?
Yes.
It's equal to,
So this will give you 2.
okay, 30 times
That gives you
2 over 30, which is 2 plus 10 I1. So let's simply get I1.
is 0.4.
I1 is simply 6.0 minus 2. Did this say 0.4?
Yes.
Okay, 10 I1 is that, okay. 10 I1 is,
0.4.
okay. So let me just do all that. 6.0 minus 2 divided by 10, or at once. You know. So that gives us 0.4 is, did you say 0.4?
Yes.
That's positive 0.4.
Yes.
And finally we just substitute it into
Original.
the original equation. So let me just, where can I bring it? Let me bring it down here so that we don't have to move into the other page. So let me bring this down here. Or let me bring, yeah, let's bring it down here. So substituting I all into equation 1. Substituting all into equation 1. So I3, we got I3 to be 2 over 30, right?
Yes.
So we have 2 over 30 equals, that's for I3. I1, we got I1 to be 0.4. So 0.4 plus I2 that we don't know.
I2 is negative.
Good. So I2 is negative. That gives us 2 over 30 minus 0.4. A negative what?
Minus 1 over 3.
Minus 1 over 3 amps. Sorry, so what's the implication?
That's we use the wrong direction.
It's actually going in the opposite direction than opposite to the direction we thought, you know. So you shouldn't bother if you are not sure about the direction, and I will tell you why. You said minus 0.3, isn't it?
Yes.
That's minus 1.3 amps.
Yes. Minus 1 here.
Minus 1 over 3 amps. So it means it is flowing. We assumed it to be going this way.
Yes.
So it's actually going this way towards the positive side of the 2 volt
Yes.
power supply. And it should be. You know, this is bigger. And this is opposing it. So which one will eventually carry the day? You know, this is, it's like you are pumping water in this direction. A smaller pump is pumping water up this direction. The bigger one will carry the day and force the water here.
Yes.
Up to meet up here.
They are not equal.
They are not equal. And if this was bigger, it would have forced the water the other way. Maybe I1 would have reversed. You know. So I2 is actually flowing in the opposite direction. So I2 is equal to 1 over 3 amps flowing in the opposite direction to the way assumed.
Yes.
So that assumes. So that's basically it. I think we can just try. So this is the way the circuit is. You can see this one has several batteries, up to 3 EMFs. E1, E2, E3.
Oh, you have 3 EMFs.
You have 3 EMFs. I think you forgot the, yeah, you
No, I didn't.
you're right. So E1, E2, E3, even if it has 10 or 20, it doesn't matter. No matter how many EMFs it has, once you follow, you apply Kirchoffs laws, you get it. It doesn't really matter. So all you need to do is treat loop by loop. There's a trick I need to show you, because you probably did not apply that trick. That's why you didn't develop an equation that will help you solve all that. Watch this. Let's see all the possible loops we can follow. Starting from this one as a reference EMF, right? I can walk, current can flow like this now, is it not? This is one loop. This is one possible way it can flow. Do you know that? Okay, by the way, you already know that from this EMF down here, E3, current can also flow like this now, is it not? This is, so we have the upper loop, right?
Yes.
We have the lower loop, right? You can even have all this, the outermost loop. Yes, you can have the outermost loop, right? You can have the outermost loop. That's probably what you didn't consider. So 3 loops: the upper loop, the lower loop, and the outermost loop. Did you get that? I represented the upper loop with green line. Let's walk around the upper loop. Let's walk around the upper loop. Are you ready? Some of the EMFs. This is an EMF there. This is another EMF there. There are only 2 EMFs in the upper loop. Am I right? So what's the value of this EMF? 6. And it is coming to the negative, so it's in the right direction. No opposing EMF. So 6 plus 2 for the EMFs, right, is equal to all the PDs. Along this route, what are the PDs? This is the first PD, which is what?
The first PD.
You know, when you go around this loop, the PDs we are meeting are these, and these. Am I right? The PDs across the, because in this kind of question it's assumed that all the EMFs have 0 internal resistance. So don't include that. That would be complications. So the only PDs we have in this upper loop are these, and this. Did you see that? Yes. These, and these are the PDs. The EMF we have there is this and this. We have already taken care of that. E1 and E2 is 6 plus 2. That's 8. Is it not?
Yes.
Okay, so the PDs are these. What's the PD here?
That's 8
I1. Is it not?
Yes, 8 I1.
Because PD is IR. V is equal to IR. So 8 IR. 8 I1. And you need to follow the direction of the arrow. If it is in the same direction as the arrow, it is positive. If it's going to oppose it, it will be negative. I will explain that to you when I get to the outer loop. Okay, so 8I1 for this. This one is what?
I1 plus I2 or I3. That's 4I3.
4I3 you mean?
Yes.
Is that what you mean?
Yes.
4I3, that's this. What about this?
Well, as close to.
So yes. So this is, let's go again for the PDs. PDs along this loop.
That's 8I1.
8I1
Plus 4I3.
plus 4I3
Plus 5I1.
plus 5I1. So 8I1 plus 4I3 plus 5I1. That is the equation for the upper loop using Kirchoffs' second law.
Okay.
Right? We can even apply the first law and derive more equations. Yes, we can apply the first law and derive more equations. I can use a different color. Okay, let's look at the lower loop. You see, when you are walking through this, always start from follow the conventional current direction. You know, conventional current direction is from positive to negative. Just like here was from positive to negative. So for the lower loop, from positive to negative. So what's the EMF in the lower loop?
That's 10.
It's only this one. This is the only EMF, the E3 is the only EMF in the lower loop. So 10 is equal to all the PDs. So let's see the PDs we are going to pass. This PD, and this PD, is it not?
Yes.
If you're going around this loop. We pass this PD, we pass this PD, and we pass this PD.
Yes.
So let's go. This one will be what?
That's 10.
10 for the...
Sorry. That's 3I2.
So we have the first PD is 3I2, that's what you have here. The second PD is...
That's 4I3.
4I3, that's what you have here. The fourth PD is
7I2.
7I2, that's what you have here. So this is the blue is the equation for the upper loop. As for the lower loop, is it not?
Yes.
We can still go around the outermost loop. Outermost loop. Ignoring this. Yes, it can work too. You can go around the outermost loop, ignoring this. That's a trick you need to know. So let's go around the outermost loop and ignore this middle root. So that is where you need to be careful. Let's start. The EMF first.
That's
6. When it comes to this,
it's
that's the direct one. 6 plus 2 because it's coming from positive to negative is the proper way. No back EMF. So 6 plus 2. And when you come to here,
that's minus.
opposing it because this one is coming to the positive side. So from positive to negative is the proper way. So 6 plus 2, they are adding up. But from positive to positive again is opposing. So that's why then we have a minus. So we have 6 plus 2, then minus 10. That's the sum of the EMFs for the outermost loop. Did you see that?
Yes.
Okay, so let's go to the PDs. Outermost loop again. The way you walked through in the EMF must be the way you walk through in the PDs.
Yes.
So let's go. All the PDs in the outermost loop.
That's
Let me trace the outermost loop again for you to see again. So all the PDs in the outermost loop. Yeah, it's there. You can see now all the PDs that we are passing through when we go through the outermost loop. Can we walk through it? We have 8I1, is it not? 8I1. Is it plus? See, the arrow is going up, so it's opposing the direction of it. This one now is opposing the direction. So it's going to be minus 3I2. Let me show you again. See the arrow is in the proper way. So that is 8I1 with a positive, right? But when we come to here, you see, can you see where the arrow is? So it's going to be minus what?
3 times I2.
So minus 3I2. That's why it is minus 3I2. After the first one is 8I1. So 8I1 minus 3I2. So let's go. Remember we started from where we have passed this. 8I1 minus 3I2 minus that because it's also opposing.
Yes.
We are moving this way, but these ones are going in the opposite direction. This is going in the opposite direction. This is also going in the opposite direction. So minus
7I2
minus 7I2. You can see it. So let's go again.
What? Minus plus. Yes, plus 5I1
because it's going in the proper direction. Beautiful. So the outermost loop We have the EMFs, 6 positive plus 2 positive in the same direction, minus 10. So 6 plus 2 minus 10. In fact, that's for the EMFs. For the PDs, this is the first PD in the proper direction, the proper arrow. 8I1 will meet this one opposite, it's opposing it because the arrow is going in the opposite direction. Minus 3I2 will meet this one, it's opposing it because the arrow is coming down instead of going in the way we are going. Minus 3I2 we go again. Sorry, minus 7I2 I meant. Minus 7I2. Then we go again. This one is going in the proper direction. Plus 5I1. All the stuff I wrote in yellow represents the outermost loop. I just simplified it. 6 plus 2 is 8, right?
Yes.
8I1 plus 5I1 will give you 13I1, is it not?
Yes.
Then plus 4I3. I call that equation 1. I simplify the blue one too. 10 is equal to, I think we have 3I2 and 7I2. That's 10I2, is it not?
Yes.
Then plus 4I3. Equation 2. Then we have the yellow one. 6 plus 2 minus 10 will give you minus 2, is it not?
Yes.
Then there are some things I can combine. I think I can combine 3I2, minus 3I2 and minus 7I2. That's minus 10I2, am I right? I can also combine 8I1 and 5I1. So I have minus 2 is equal to 13I1 minus 10I2. Check it out. I just simplified all this equation. The yellow one simplified to here. The blue one simplified here. The green simplified here. Can you see? All we just need to do is to solve this simultaneous equation. All 3 equations, and it can be solved. We have a I can even add another equation applying Kirchoffs' first law, looking at the junction. For instance, consider this junction. At this junction, let me use a red line to do it. At this junction, let's call it junction L, junction P. Applying Kirchoffs' first law. Total current flowing into a junction is equal to total current flowing out of the junction, is it not?
Yes.
So what should we say?
That's I1 plus I2.
I1 plus I2 are all flowing in is equal to I3. So we can use that too. I1 plus I2 is equal to I3. You can use that. You can even add that as one of the equations. You know. So, or since I3 is equal to I1 plus I2. You can call that equation 4. You can develop as many equations as possible. We may not even need this, and we can still solve it without even using this. For instance, these 3 equations can be solved. Let me see. We can make, I have I1 and I3 here, right?
Yes.
I have I2 and I3 here. So I will just make I2 solve the formula in equation 3. So that I will work with the green and the blue. Let me show you what. You know equation, you find your way around it. So from, let me just write, from equation 3, equation what, 3, right?
Yes.
Let's make I2 say the formula. I2 is equal to what?
That's
10I, let me just write 10I2 is equal to 13I1 plus 2, or 2 plus 13I1. I'm just solving this equation, sorry. They want the yellow. Making 10I2, if I take 10I2 to the other side, 13I1 is already here, 2 will cross over, just to simplify it. Did you get that?
yes.
So I2 is equal to what? 13I1 plus 2 divided by 10, is it not?
Yes.
You can call that equation 5 if you like. Why am I doing that? So that I can only have in 2 terms and solve the simultaneous equation. This one has I1 and I3. This one has I3, so I just put all this one in terms of I1. Do you get my point? So are you sure you're getting it? So let's rewrite equation 2. Equation 2. so that I won't have I2 again there. Anywhere I see I2, anywhere I see I2, this is what I will write there, is it not? So substituting, let me say substituting equation 5 into equation 2, or substituting I2, substituting equation 5 into equation 2, yes. That's this equation 5. We are going to use it to replace. I could have just let me leave it as there's no point. This one has 10 I2, so there's no point. It's better to leave it the way it was. I don't know if you have observed what I mean. We have 10 I2 there, so I don't need to change it, simplify it. So I just leave it as. So this is equation 5. Substituting. So this is the real equation 5 I need. Substituting equation 5 into equation 2, right? Yeah. Wherever I have 10 I2, what should I replace there? Substitute that. Yeah. So that gives me now, what color can I use now? Let me use red. Let me use red. So 10, right, yeah, is equal to, instead of I2, what will I write now? 13 I1 plus 2. So 13 I1 plus 2, then plus 4 I3. Is it not?
Yes.
So let's just simplify so that all of them will be in the same straight line. 10 plus 2 is 10 minus 2 is 8, isn't it?
Yes.
So 8 is equal to 13 I1 plus 4 I3. We can also try substituting this to know if it will work. This is supposed to be 2 plus 2, and mistakenly wrote 3. You know, I3 is equal to I1 plus I2, is it not? I1 plus I2. We can even make, I think this is the one we probably should have used.
From stuff.
This is the one we can substitute into this. Do you understand?
Yes.
This equation, let me show you. This equation has I1 and I2. I mean the yellow one. Can you see? It has I1 and I2, right?
Yes.
The blue one has I2 and I3. So why not just substitute the I3? So that it will be in terms of both I1 and I2 and solve this continuous equation. So I can also try that. Let me also say, write it down here, just for record purposes. From substitutes, let me call that. It's all about solving simultaneous equation, which you can always solve, is it not? Substitute I3 in equation 4 into, let's try that, into equation 2, right? Substitute I3 in equation 4 into equation 2. I3 in equation 4 into equation 2. That will give us 10 is equal to 10 is equal to 10I2, 10I2. 10I2 plus, instead of 4I3, I will now have 4 opening bracket I1 plus I2. I don't know if you can see what I mean. Alright, so we now have this equation in green, this second equation in green, and the first, and the one in blue, and the one in what? And the one in yellow. We use the one in yellow and the one in green. We are solving the one in yellow and the one in green. Please read it out to me. Let me write it in the opposite page. Minus 2 is equal to, the one in yellow is minus 2 equal to 10I1. Let me write it. Minus 2 minus 2 is equal to 10 I1 minus 2 is equal to 10 I1. Oh, minus equal to 13 I1 minus 10 I2. 13 I1. 13 I1 minus 10 I2 minus 10 I2. That's equation 1. Let's use this one as equation 1. Then the other one is the green one we got. 10 is equal to 10 I2 plus, I think, let me zoom it in a bit. Can you write it down so that I won't have to be opening the button? 10, this green one. 10, use the other marker.
What is it?
10 is equal to 10 I2 plus 4 I1, opening the bracket, or 4 plus I2. Okay, so let me just write it in the opposite page. So that's the green one, right?
Yes.
10 is equal to 10 I2, right?
Yes.
10 I2 plus 4, open the bracket, I1 plus I2. So let's open the bracket. That gives us 10 is equal to 10 I2, right?
Yes.
Plus 4 I1 plus 4 I2, is it not?
Yes.
So that will give us 10 is equal to 14 I2, am I right?
Plus 14 I. Sorry, plus 4 I.
Plus 4 I1. So we use these two equations. Let's just rearrange it so that you can use the calculator to solve it. I want to rearrange it so that I1 will come up first before I2. So that we just use the calculator to solve it. Do you get that?
Yes.
So 10 is equal to 4 I1, is it not?
Yes.
Plus 14 I2. Let's call this one now equation 6 or 7 or whatever. So you just use your calculator and solve these two simultaneous equations. That's the one we should have used instead. So that Kirchoffs' first law was helpful. You can impute all that, right? Then 13 minus 10. You know the constant comes later, you know what to do. So, just solving the simultaneous equation, these two. So, what the idea is solve the simultaneous equations.
Alpha
And 7. So I1 is what? I1 is the first variable from your calculator.
I1 is 12 over 37.
12 over 37, right?
Yes.
So I1 is 12 over 37. So it actually worked. 12 over 37 amps. While I2 is what?
So it's 3 over 37.
Beautiful. So I2 is 23 over 37. 23 over 37 amps. So you can just substitute into this equation. The Kirchoffs' first law we applied here. What equation do you call it, by the way? Equation 4, right?
Yes.
You get I3. I3 is just I1 plus I2, is it not?
Yes.
I3 is I1
Okay.
plus I2. So let's just do that. I3 is I1 plus I2. So I3 is equal to I1 plus I2, which will give us 12 over 37. I think that's just 40. It's a simple arithmetic. 12 over 37 plus 23 over 37, you said?
Yes.
And what does that give us?
34 over
35.
35.
35 over 37. 35 over 37 amps. That does it. Tell you. So, you can see the analysis.
Yes.
where we analyzed all obtaining different equations 1, 2, 3, 4, 5, and just simply solving equations until we were able to get 2 equations that we needed, equations 1 and 7, and then we solved equation 1 and 7 simultaneously to get all the answers and substituted. That's basically it. In whichever form it comes, the only thing you need to be careful about is how to follow the loops, whether for EMF, like the upper loop, the lower loop, or the outermost loop, or even applying Kirchoffs' first law. We follow loops with Kirchoffs' second law, but if it is Kirchoffs' first law, you look at junctions, because at this junction, I1 and I2 we must be equal to I3 where they split. Once you apply first law, second law, and obtain equations, solve the simultaneous equations, you'll get your answer. Please don't forget to like, subscribe, and comment. Thank you so much.
Welcome to Like Learning School, your premier online education platform. At Like Learning School, we are dedicated to helping students and learners unlock their full potential, providing them with the foundation, support, and guidance they need for academic excellence. Our platform caters to 2 main target audiences. Firstly, we work with school children of all ages, offering academic follow-up and accountability partnerships. Our seasoned tutors provide personalized attention to ensure students stay on track and reach their goals. Secondly, we support students and learners who are preparing for internal, external, entrance, or professional examinations. We offer comprehensive and well-structured support to help them achieve outstanding performance in their exams. Our robust virtual courses are designed to keep students engaged and motivated. With interactive videos showcasing our teaching sessions, students actively participate in the learning process, making education enjoyable and effective. But that's not all. We believe in personalized education. Our students have access to personalized tutorial sessions, whether online, physical, or hybrid, tailored to their unique learning needs. Join us at Like Learning School and experience a transformative education journey. Visit our website at www.likelearningschool.com or contact us at +234 808 509 5144 to learn more and get started today.